All right, welcome to The Explainer. Today we're going to lift the hood on artificial intelligence, right? We're going to find out what the engine is that powers how it actually learns. And we're talking about something called optimizers. These are the clever little algorithms that take a model from knowing nothing to being, incredibly smart, one tiny step at a time.
So here's how we're going to break it down. We'll kick things off with the basic idea, this downhill journey. Then we'll see how we can give it a push by gaining momentum. After that, we'll talk about adaptive learning rates, basically making it smarter. We'll even ask, is there a single ultimate optimizer? And then we'll put it all together to see what this stuff looks like in the real world.
Yeah, this is really the big question, isn't it? At its core, how does an AI model actually learn? How does a jumble of digital neurons go from just making random guesses to, being able to spot a cat in a video? Well, the secret is this really cool process of guided trial and error. And the whole thing is driven by an algorithm we're going to get to know very well, gradient descent.
All right, let's start that downhill journey. We're jumping right into gradient descent. And this is the absolute foundation of almost all modern AI training. But the funny thing is, the core idea behind it, it's brilliantly simple.
So here's the deal. Every single time a model gets something wrong, we can measure how wrong it was. We use something called a cost function for that. Just think of the cost function as telling you how high up on a hill you are. A big mistake means you're way up at the peak. A small mistake, you're near the bottom. And gradient descent, well, that's just the fancy name for the process of looking around, figuring out which way is downhill, and taking a small step in that direction. We just keep doing that, rolling the ball a little closer to the bottom each time.
Seriously, this ball rolling down a hill idea is the key to all of this. Just lock that image in your mind. The entire landscape of the hill, all its bumps and valleys, that represents every possible way we could set up our AI. And the height at any given spot? That's just how big the AI's error is. So the goal of the game is simple. Get that ball to the absolute lowest point in the entire valley. That's the sweet spot, the point of minimum error. And we want to get there as fast as we can.
Okay, but you can probably guess that this journey isn't always so easy, right? It's not always a nice, smooth slope. And that brings us to the first really big problem we had to solve and the first major innovation that helps our little ball get to the bottom without, getting lost or stuck.
So what happens when the hill gets tricky? What if it has these long, skinny ravines or these wide, flat plateaus? This is where the basic version, what people call vanilla gradient descent, really starts to struggle. In a narrow ravine, the ball just bounces back and forth between the walls, making painfully slow progress downwards. And on a flat spot, the slope is practically zero, so the ball just stops. It thinks it's at the bottom, but it's not even close.
So, how do we fix this? The answer is momentum. The idea is to give our ball a little push. It's a way to speed up the process, especially a common version called stochastic gradient descent, or SGD. It's so clever. It basically remembers the direction it was just going and adds a little bit of that past movement to the next step. So now it can just power right through those flat spots, and it helps smooth out all that zigzagging in the ravines. Honestly, this was a massive breakthrough. It meant models could learn way faster and were much less likely to get stuck. This really opened the door for the incredibly deep and complex networks we see all over the place today.
It's just like a real ball rolling down a hill, right? It starts to build up speed. So when the path is consistently downhill in one direction, the ball gets faster and faster. The updates get bigger. But in those directions where the slope keeps changing, like when it's bouncing off the walls of that ravine, those back and forth updates start to cancel each other out. The end result? A much smoother, more stable, and faster path to the bottom.
But wait, we can make this ball even smarter. There's an approach called Nesterov Accelerated Gradient, or NAG for short. It's a really clever twist. Instead of just calculating the slope where it is right now, the ball first makes a jump based on its momentum, and then it looks at the slope from that new, future position. This gives it a kind of look-ahead superpower. So if it jumps forward and sees the hill is about to go up, it knows to pull back and slow down before it overshoots. Super smart.
Okay, so momentum is great for helping us navigate tricky terrain. But what if the terrain itself is just weird, like really bizarrely shaped? This leads us to the next big challenge. What do you do when the hill has super steep cliffs in one direction, but gentle rolling slopes in another? Yeah, just picture it. A landscape with a massive cliff on one side and a barely there slope on the other. If we use the same step size, the same learning rate for everything, it's just a recipe for disaster. We'd take this giant leap down the cliff and probably fly right past the bottom. But on the gentle slope, that same step size would be so tiny we'd barely move at all. It would take forever. Clearly, a one-size-fits-all approach just isn't going to cut it.
We need to adapt.
And that's exactly where adaptive learning rates come into play. The idea is simple but powerful. Instead of one learning rate for the whole model, we give every single parameter its own personal learning rate. And this was a total game changer, especially for things like understanding language. Think about it. In a text, some words like the and a show up all the time, while other words are super rare. It makes sense to treat them differently, right?
The first big algorithm to try this was called ADAgrad. It had a neat idea. It kept a running tally of all the past updates for each parameter. If a parameter had a history of big updates, ADAgrad would shrink its learning rate. The problem? Well, that was also its fatal flaw. It accumulated everything and never forgot. So over time, the learning rates for every parameter would just get smaller and smaller and smaller until eventually the model just stopped learning altogether. It basically froze in place. Oops. So, naturally, this led to some quick fixes. An algorithm called RMSprop, which was famously just mentioned in a lecture by AI legend Jeff Hinton, solved ADAgrad's big problem. How? It just looked at a recent average of the past updates, not the entire ever-growing history. It had a shorter memory. Then AdaDelta took it a step further. It used a similar idea but managed to get rid of the need to set a base learning rate at all, so the whole process became even more hands-off and automated.
Okay, let's take a quick breath. So we've got two big ideas on the table, right? First, there's momentum, which helps speed things up and get us through tough spots. Second, we have adaptive learning rates, which customize the step size for every single part of our model. So the next logical question is pretty obvious, isn't it? What if we just combined them?
And boom, that brings us to ADAM. It stands for Adaptive Moment Estimation. And let me tell you, this thing became the default choice for training deep neural networks for a very, very good reason. It does exactly what we just talked about. It takes the absolute best of both worlds. The beauty of ADAM is just how elegantly it stitches these two ideas together. So, on one hand, it keeps track of the average of the gradients, what mathematicians call the first moment. This part acts just like the momentum we saw earlier, giving our ball that forward push. But at the same time, it also keeps track of the average of the squared gradients, the second moment. And that's what gives it the power of adaptive methods, scaling the learning rate for each parameter individually.
And of course, people didn't just stop there. Innovation keeps on rolling. The next logical step was an optimizer called NADAM. And you can probably guess what it does. It takes the super clever look-ahead trick from Nestrov's method and bakes it right into ADAM. The result? An even smarter, even more powerful optimizer.
All right, that was a lot of theory. We've gone all the way from a simple ball rolling down a hill to this super sophisticated system with momentum, look-ahead abilities, and custom step sizes. But what does it all actually look like? How do these things really perform when the rubber meets the road?
And check this out. These images show the difference perfectly. Look at the picture on the left. That's a tricky spot called a saddle point. See how the momentum and nag methods, the green and purple paths, are really struggling to figure out which way to go. They almost get stuck. But the adaptive methods in blue and yellow, they just find the right path and dive straight down. And now look at the one on the right, in that narrow ravine. Again, you can see momentum and nag get thrown off track at the start, kind of bouncing around. Meanwhile, the adaptive guys, they just chart a much more direct, confident path right to the middle. It's a night and day difference.
So what's the bottom line here? What's the practical takeaway for you? Well, look, the simple, basic method can sometimes get the job done. But man, it can be slow, and it often gets stuck. If you're working with a big, complex deep learning network where training time really matters, an adaptive method is almost always your best bet. In fact, the people who invented ADAM even said it themselves. For most problems, ADAM is probably the best overall choice to try first.
And this brings us right to the frontier, to the edge of what we currently know. Because even with these amazing optimizers, the whole process is still step-by-step. It's sequential. You have to feed the data all the way through the network, from beginning to end, calculate the error, and then send that error signal all the way back before you can make a single update. It's called the locking problem because the front of the network is locked until the back is done. And figuring out a way around that, finding a way for an AI to learn that isn't so rigid, something that might be a little more like how our own incredibly complex brains work, well, that's one of the next great, exciting challenges in the world of AI research.